Sketching of curves is not a negotiable skill. It is something that you need to do for coordinate geometry. It's going to come back in functions. It's going to rear its head in differentiation and in integration. And of course, it links into sketching your trig functions right at the end. So it is really, really a good idea if you get used to it now, get the basic set of skills, and then you can move forward with it as you move through your course. So, sketching curves. Okay, there's an important, very big clue here in the title. We are sketching. We are not plotting. So there's no graph paper, there's no grid paper, there's no tables of values, there's no calculations. We just need a ruler, a pencil, and a pen. Okay, because what we're going to do is we're going to sketch these graphs from their key features rather than plotting them accurately from points on the graph. So to remind you, we have no graph paper, no grid paper, no tables of values, no list of coordinates. We need a ruler, a pencil, and a pen. Okay, we do need to take note, things like our axes need to be drawn in pencil. Let's rather than get a pencil-like color going. Okay, here we go. Drawing our axes with a pencil and a ruler, because of course we can be sketching for marks. Often we sketch for our own personal interest and understanding of the question, but we can also sketch for marks. So ruler and a pencil, we label with a pen, and we don't label all of our axes. We're only going to label important points. We don't go 1, 2, 3, 1, 2, 3, -1, -2, you know, because that's working then at the level of accuracy that we're not working at, okay? We're sketching. So we're just giving a general idea of what this graph is going to look like. So when it comes to a straight line, it's straightforward. Then, as you're familiar, we put it into y equals mx plus c. We find our intercept, and we move our gradient. And whoops, there's a straight line, finished. When it comes to curves, life is far more interesting. Okay, because we don't have a y equals mx plus c equivalent for our curves. What we're looking for is the important features. Okay, so what are the important features of our curves that we're looking for when we want to now go and sketch? First thing, we need to look for the intersection with the y-axis. What is lovely is this is also still our constant term. Same like it was a plus c in the y equals mx plus c. Our constant term in our curve is also our intersection with the y-axis. Intersection with the x-axis. It's another very important feature, and there we're looking for a factorized form. And often you'll find if you're sketching a graph, you're given that graph in factorized form, or given the function in factorized form, because then you can see straight away what's my intersections with the x-axis. Third one is stationary points. The vertices of a curve, the turning points of the curve, the maximums and the minimums, those are really important features of a curve. So when we're working now in coordinate geometry, we don't pay as much attention to this as we do when we get into calculus, into differentiation and integration, because differentiation, a large focus of that is actually locating these stationary points. Okay, so we would think there in terms of, oh, let's actually put this here, hold on. This is the constant term. This is we're using our factorized form. Stationary points, now we're talking differentiation. But keep an eye out, because if your curve is a quadratic, then you can also use completed square format. Because remember, you can always get that coordinates of that vertex straight out of the completed square format. And if you've got the coordinates of the vertex, then you have the coordinates of that stationary point. The last piece of important feature that we're going to use to sketch our curves is the general shape. So looking at the function that we're working with, is it a quadratic, a cubic, a quartic, and then what is the general shape for that type of curve? And when we put all of this information together, then sketching becomes a whole lot more straightforward. So let us take a moment to have a look at these general shapes. So we're going to look at a few different things. We're going to look at if we have plus x to an even exponent. So x squared, 3x squared, 4x to the 6, x to the 4. Okay, so our exponent is even and our coefficient of this highest exponent term is positive. We're going to contrast that with minus x to the even. So again, exponents 2, 4, 6, 8, and so on. But now we have a negative coefficient for our highest exponent term. So if we think about it, we have x squared. Okay, it's a smiley face. And what's really cool is that they're all smiley faces, and they're all sad faces. Now, why the dotted line? Okay? The dotted line is because we have a maximum number of stationary points. And that equals n minus 1, where n is your exponent. So if you're working with a x squared, then you would have maximum 1 stationary point. So you would have, e.g., x squared, 1 stationary point. X to the 4 would go 1, 2, 3 stationary points. X to the 6, maximum of 1, 2, 3, 4, 5 stationary points. And the same here. So e.g., minus x squared, 1 stationary point. Minus x to the 4, 1, 2, 3 stationary points. But we're maintaining that smiley face and sad face. It's just the number of wobbles in the middle can vary depending on that maximum number of stationary points. So if we do a similar thing now for plus x to the odd and minus x to the odd. So here we're now talking about x cubed, x to the 5, x to the 7. Also, funnily enough, x to the 1, our linear behaves in exactly the same way. So if we think about if we had plus mx, we're going up to the right. So if we turn it into a curve, we're going to dip, but carry on going up. So if it's at a minus, we're coming down. We're going to dip, but we're going to carry on down. And again, that number of wobbles in the middle, the number of stationary points, is going to vary depending on that exponent. So e.g., x cubed would be exactly sort of like what we've drawn here, because it's 1, 2 stationary points max. X to the 5 would be 1, 2, 3, 4. Okay, because maximum 5 minus 1, 4 stationary points. So e.g., minus x cubed is actually what we've drawn there with 2 stationary points. Minus x to the 5, 1, 2, 3, 4. Okay, so when we add in other terms, If we've got an x to the 5 function, we can have an x to the 4, an x to the 3, an x to the 2, and an x term as well as that constant term. And different interactions between those different terms are going to do different things to our curve. So we could lose stationary points. We could have a cubic graph with 1 stationary point. Okay, so that's why we say it's the maximum number of stationary points. That is n minus 1. That gives us our general shape. But whenever you're doing this, keep a very careful eye on those x-axis intersections, because that's going to give you a very good indication of how many times you're wobbling across that x-axis. These are the general shapes that are explicitly included in your syllabus. But there are another set of general shapes that are going to come up, so it is well worth getting to know them too. And that is your reciprocal graphs. Your reciprocal graphs often sneak in with functions, so it's important to be happy and aware of them and know what it means when you see a 1 over x or 1 over x squared. What are you looking at? Okay, so we have 1 over x to the even, and we have 1 over x to the odd. So 1 over x, 1 over x cubed, 1 over x to the 5, and up here 1 over x squared, 1 over x to the 4, 1 over x to the 6. Okay, so we're just splitting between those two, and what we get is 2 different patterns. 1 over x to the even is going to give us a graph which is entirely above the x-axis. Okay, even number. So every negative value is going to be squared. It's going to give a positive output. So even when x is a negative value, it's going to have a positive output. Okay, 1 over x to the odd is going to give us then maintaining those signs. Positive x's give positive y's, negative x's give negative y's. And in both cases, the y-axis is an asymptote. We don't cross it. Now, and when we get to functions and we get to play with shifting our graphs up and down and all over the place, and then we can cross that axis. But our general plane graph doesn't cross the axis. So if we flip this around again, we considered plus and minus on the last one. So minus 1 over x to the even and minus 1 over x to the odd. What happens here? Well, everything that was positive is going to become negative. So we're just going to sit underneath instead. Everything that was positive will become negative. Everything that was negative will become positive. So we also just flip over that x-axis. So when it comes to reciprocal graphs, it's really important to understand that now you're working with graphs with an asymptote in them. We're not going to cross certain vertical lines. In this case, with our plane ones, it's all about that y-axis. We're not going to cross it. Okay, and then it's that impact of that even power or the odd power. So are your negative values maintained for negative answers, or are your positive values giving you only positive answers? And your negative values only giving you positive answers because you're working with an even exponent. So reciprocal graphs, something to be well aware of. So now I've just got a few examples to work through to give you an idea of what sort of things you can work with when it comes to sketching and how you systematically work through sketching a graph. We're going to start with y equals 1 minus 2x, x plus 3. So remember we had those 4 pieces of information about those important features, right? So the first one was our y-intercept, the constant term. Now the only way that you can make a constant term out of this is if you look just at the ones with a constant, because any other multiplication is going to give you x's in. So it's just 1 times 3. Our x-intercepts Well, we've got two brackets. Each of them can be equated to 1. So from our first bracket, we would have x equals a half. From our second bracket, we'd have x equals minus 3. The third thing we said that we wanted to look for, working off this at the beginning, is stationary points. Now, when it comes to this, it is a quadratic, but we haven't been working with it in completed square format already. So we're not going to worry too much about completing the square at the moment. And then our last one is our general shape. So what is our maximum exponent? That would be our minus 2x times our x, would be an x squared, but it would be a minus 2x times x, it would be a minus x squared, which means it's a sad face. So now we're ready to get out our ruler and our pencil. And we draw ourselves some axes to work with. Then we get out our pen. In order to label things, we're plotting y against x is our axis. Now we get to sketch. So y-intercept is 3. So let's say roughly 1, 2, 3 is up here. X-intercepts are half and minus 3. So we did a little bit of a dodgy. Let's just move this one across. So you do want to have a think before you do this. See? Okay, doesn't want to move my x, so I shall redraw my x. You learn new things every day. Okay, drawing and x. There we go. Okay, so if that is 3, then that is roughly a half. And then 1, 2, minus 3 down here. So now we can see we've got a good idea of where we're heading. So we go back to our pencil, roughly aiming for halfway in here to make that highest point of our curve. Okay, and then we go up through our rough middle, through our 3, and down. This is atrocious. Okay, it's much easier to do this with a pencil on a paper. Let's give it another try. Up, and through, and down. Okay, so you have to believe me that those ones are going through. In the meantime, let's try a little bit of a cheat. Not like that. So we shall now move the half to here. So it does go through a half. But it is easier to do these on pencil. And if you are struggling, like I'm obviously struggling, then the idea is to sit down and do a whole lot of sketching and get practice. Okay, we want to label y equals 1 minus 2x, x plus 3, because every time we sketch a curve, we might be sketching out a curve, we might be sketching out a line with it. So you want to have that habit created of always labeling what you've sketched. Are we happy? Okay, we're looking good, so let's do another one. Y equals x squared minus 4x plus 3. Well, if we look at this one, we can see straight away our y-intercept equals 3, because now we've got that constant term sitting there. In order to get our x-intercepts, we're going to need y equals factors of 3 that add to 4 is easy. X and 3, x and 1, same signs, negative. So our x-intercepts equals 3 and 1. So in this case, it's so much easier to factorize and to put it into the computed square format. So we're not going to bother about the stationary point again. We're just going to work with those two intercepts. Okay, but we know that if we're halfway between 1 and 3, then we are at 2. So we know that line of symmetry is going to be at x equals 2. Okay, so last one, we're not going to do this. We haven't built into it. And we have a quadratic. In this case, a happy quadratic. So a smiley face. So we head back now to our axes and we think of it first. Y-intercept is 3, X is 1 and 3. So we're working only in that everybody positive quadrant. So there they are. Okay, ruler and a pencil to draw those, and then back to, whoopsie, to a pen to do your labeling. Roughly 1, 2, 3. So roughly 1, 2, 3. Back then to pencil to do the sketching. Happy face, turning point in the middle of 1 and 3. So down from the 3 to the 1, through that 2, and back up again, a beautiful symmetrical curve. Much better. You see, practice does make perfect. We will get there eventually. I shall be doing stunning graphs on a digital pad, and you shall be doing stunning graphs on a piece of paper. Okay, so there we have another example. We worked through the important features and then we went and sketched. So something a little bit different. Y equals X, X minus 1, X plus 1. This is a Dow difference setup. So let us think through those same steps. First step, how are we going to make our intercept on the y-axis with the constant terms, right? But we've got to think about this guy here. Because this one here is actually hiding in there an x plus a 0. So if we now combine all of those constants, we have a y-intercept of 0. Our x-intercepts, in this case, we're going to be 0, 1, and minus 1. So minus 1, 0, 1 makes it easier for us if they're out in order. That little x at the beginning mustn't be ignored. Stationary points for a cubic without differentiation. Now we're not going to bother with that one. So last one then is our general shape. So the biggest exponent we could have is the x times the x times the x is an x cubed. And it is happy, those are all positive. So our general shape is that. And it looks rather interesting because 1, 2, 3, 1, 2, 3. So it looks like we are going to cross that x-axis 3 times and we're going to have that classic shape. So ruler and pencil giving us some axes to work with. Back to then a pen to label. We have y, we have x. We need a 0, we need a minus 1, and we need a 1. And then we just think, and we go up, we go down, we go up, and it does work. Isn't it wonderful? So back to our pencil then. So we're going up through the minus 1, because it's a positive x squared, but then we're ducking down to go through the 0, and then we're ducking back up again to go through the 1. And you see why we can't have any labels on that y-axis, because we don't know the height of those stationary points. We don't know if they're little tiny short little bubbles or great big bubbles. So the fact that we haven't put any information on that y-axis means that we don't have to put them in the right place, because we're not saying they're at this point. We're saying they are going up and down. We're just looking at the general shape of this graph. And they're just sketching the graph. Okay, we've got one more interesting one to go. We'll fit it in quickly. So we have y equals x squared minus 1, 4 minus x squared. Now when you see something like this, your brain should be going, hold on, hold on. I must think a bit here because those I recognize. Both of those brackets are a difference between two squares. So y equals x plus 1, x minus 1. This is also a difference between two squares. 2 minus x, 2 plus x. Now we work through our steps. So first step, our y-intercept. We take all the numbers from all the brackets, we multiply them together. So 1 times minus 1 is minus 1. Times 2 is minus 2. Times 2 is minus 4. X-intercepts. 1 from each bracket. So we would have minus 1 and plus 1. And we would have minus 2 and 2. So minus 2, minus 1, 1, and 2. Yes. Okay. Stationary points without differentiation, we're not going to go there. So our last one is our general shape. So x times minus x times x would give us up minus x to the 4. So in sad face territory, but with 3 maximum stationary points. And if we look, we've got 3 x-intercepts, 4 x-intercepts, 1, 2, 3, 4 times we're going to cross. So this is looking very much like we're going to get a classic shape. Ruler and pencil for some axes. Okay, we're going with an intercept of minus 4. So we want to have our axis relatively high up. Back to a pen for labeling, plotting y against x. Then we're going 1, 2, 3, minus 4, minus 1, minus 2, 1, and 2. Then we just look in our heads first. We go up, we come down, we go across, we go up, we come down. It does work. So we start from low. We go up, down through the minus 1, across the axis at the minus 4, up through the 1, and down through the 2. And there we have our sketch of y equals x squared minus 1, 4 minus x squared, and nobody squealed. We shall go back here. Y equals x, x minus 1, x plus 1, because we do label every curve we sketch. Whether it's a quadratic or a cubic or a quartic, the same rules apply. So make sure you make friends with sketching curves.